Let's begin our study of integral calculus, as opposed to differential calculus, with a brief review of what we learned in the first quarter of calculus, differential calculus. What was the key question that we tried to answer? It was, how do we find the slope of a line tangent to a curve at a point? There were a few tangent line questions we could solve without the use of calculus, which we developed to solve that tangent line problem. Here, for example, is a circle of radius 5, and if we choose a point on the circle, say 3, 4, we can remember from geometry that the tangent line to a circle must be perpendicular to a radial line of a circle. That's something we can prove just using geometry. Here's the radial line at this point. It has a slope of 4/3 because we go over 3 and up 4. So a tangent line must have a slope of -3/4, and there we go. So that was a special case. For a more general case, such as this parabola, if we choose a very special point, we might guess that the slope of the line tangent to the curve at this point is 0. But for most arbitrary points, solving that problem wasn't quite so easy. So what we did was we added a second point that was near our first point, and then we drew the line that passed through those 2 points. We called it a secant line. And then we let the second point get closer and closer and closer to the first point. And once we took that limit, we called that limiting slope the slope of the tangent line. Or we called it the derivative of the function at that point. And once we were able to do that for any point on the curve, we then looked at other functions. And we spent a good deal of time developing shortcuts to finding those derivatives of common functions. One of the applications of a derivative was to locate points on a curve that were a local minimum or maybe a local maximum of the function. And we did that by looking for places where the tangent line was horizontal, where it had slope or derivative 0, where the function had derivative 0. Another application was to think of, say, this function as the position function of this point as time moves along. And if we do that, we can see this point moving along here. Sometimes it's moving up, and it reaches a maximum height right here, and then it starts going down, and so forth. And what we're able to do is determine the velocity of this particle by looking at the slope of the tangent line, because the velocity is the rate of change of the position function, the height function in this case, and it's the derivative of that height function. Let's turn that around now. What if we know the velocity of a particle? Say that velocity is 5 meters per second, and it has constant velocity from 0 to 4 seconds. What would we do to compute the distance that this particle travels? Well, we would say that the velocity is 5 meters per second times 4 seconds. We cancel those units. We get the distance is 20 meters. So what we're really doing is we're finding the area under this constant function, because we multiplied 5, the velocity, times 4, the change in time, and we got 20. This rectangle here has area 20, and it corresponds to the distance the particle travels if this function is a velocity function. Now, what if we have a different velocity function, one that's not constant? We might hypothesize that the distance the particle travels is equal to the area under this curve as well, this graph. And if that's the case, then this triangular region has area of 1/2 times 4 times 5. So in this instance, the distance traveled would be 1/2 times 5 meters per second times 4 seconds, and that gives us 10 meters. the particle is slowing down, its velocity is getting smaller. So instead of traveling 20 meters as it would have if the particle had kept traveling at 5 meters per second, it travels half that distance. Seems reasonable. But what if we have a velocity function that looks like this, and we want to find the area under this curve to find the distance the particle travels? This is not so easy. We might say to ourselves, well, it has to be bigger than 10, and it has to be less than 20, so this distance the particle travels is somewhere between 10 and 20, but how do we know what it is exactly? Well, that's what we're going to be tackling here in integral calculus. Now, before we get to this problem, let's review a few things that we know about areas of geometric figures. One of the simplest geometric figures that we know how to find an area for is a rectangle. Here's one right here. It has base 3 and height 5, so the area would be 15. In general, if we have a rectangle with base B, height h, the area is b times h. Not surprising. Notice that 3 times 5 is 15, and we have exactly 15 unit squares inside this rectangle. If we change the height or the base of the rectangle, we can still use the same formula, base times height. What if we cut that rectangle in half? We'd have a triangle. And what would the area of this triangle be? It would be half the area of the rectangle. It would be 1/2 times the base times the height. Another familiar formula. What if we look at a more general triangle? Here's one. Its area is still 1/2 the base times the height. We could easily prove that based upon our previous triangle area formula. And that works no matter what this other part of the triangle looks like. What if we did this? What if we put a rectangle in the middle of these two triangles? Now we have a figure called a trapezoid. What's the area of this trapezoid? Well, it's the area of a rectangle plus the area of this triangle plus the area of this triangle. So you could easily find that yourself. We could also develop a formula for the area of a trapezoid. It turns out in general that if we have a trapezoid with a bottom base capital B and a top base little b and a height h, that the area of this trapezoid is the average of the top and bottom lengths times the height. Again, you can prove that using the formula for area of a triangle. What if we looked at a slightly different trapezoid? Let's look at this one. Here, the base is the constant on the top and the bottom, if we think about it in a certain way. The heights are different, though. What do we have here? It's called the little height h and the big height big H. Here's the base. The area is the base times the average of the two heights. You can perhaps see that more easily if you add in the average height. This side has a height of 8, side has a height of 11, halfway in between is 9.5, and so this trapezoid is going to have the same area as a rectangle of height 9.5 and base 5. Well, what about circles? Do we know what the area of a circle is? You probably remember the formula, but before we think about the area of a circle, let's remind ourselves that the circumference of the circle, the distance all the way around the circle, is defined to be pi times the diameter. Actually, pi is defined as the ratio of the circumference of a circle to its diameter. But the circumference formula then can also be written as pi times twice the radius, because a radius is half the diameter. So we get the familiar formula, circumference equals 2 pi r. But what about the area of the region inside the circle, which we might call a disk? We could cut the circle into pieces, or the disk into pieces, in a certain unusual way. We could chop this disk into a bunch of little rings like this. And then we could take each of these rings and we could unwrap them, and each one would turn into a rectangle if we unwrapped it. And we could keep doing that with more and more ring slices, and we get more and more rectangles, but they would be thinner and thinner. After we create a very fine partition of this disk, these rectangles over here seem to form a triangle. What would the area of that triangle be? Well, the radius of the circle is the same thing as the base of the triangle, because all of these little rings get unwound and stack on top of the radius. The height of the triangle turns out to be the circumference of the circle, because we've unwrapped this outermost ring and it becomes the rightmost rectangle. So what's the area of this triangle? Here's our triangle. The base is the radius of the circle. The height is the circumference of the circle, or 2 pi r. So the area here is 1/2 the base times the height, or if we simplify it, pi times r squared, and that's our familiar formula for the area inside a circle. In fact, circles come from triangles in this viewpoint, and triangles come from rectangles, so we're back to rectangles again. Then we could build other figures. For example, here's a rectangle with a half disk mounted on top. I bet you could find the area of this thing. Here we have half of the disk, so that would be half of pi r squared. If we have other fractions of circles, sectors of circles like this, we can come up with a formula for the area of a sector of a circle by thinking of what fraction of the circle we've cut off with this sector. This seems to be about 1/8 of the circle, 1/8 of the way around. This angle right here would be about pi over 4, measured in radians. Remember, a radian is the distance along the unit circle of this arc that's the outer boundary of this sector. In general, if we have an angle theta here, this is our radius of the circle, this is theta. The fraction that we've shaded here in the sector is theta out of 2 pi radians that takes us all the way around the circle. So that's the fraction of the total area, which is pi r squared. We cancel the pi's, and we get an area here that is 1/2 r squared theta. You may remember that from geometry or trigonometry. We don't really have to memorize it, though, because we can always work it out this way. Let's look at one more area problem. Here's part of a circle. I want to cut off the region in the first quadrant that is inside this circle, but to the left of this line. That region right there. How would we find the area of that region? Well, if we're a little bit clever, we can actually figure this out using what we already know. We can cut this region into 2 pieces. A piece that is a triangle, and another piece that happens to be a sector of that circle. Let's look at this more carefully. Here's part of our circle. Here's the y-axis. Here's our other line. I'm going to call this distance right here A, and we've split it into 2 pieces. Here's our triangle piece, drawn a little bit bigger. The bottom is A. The hypotenuse is 1, because it's the radius of our unit circle. This other side has to have height square root of 1 minus a squared due to the Pythagorean theorem. So the area of the triangle part is 1/2 a times the square root of 1 minus a squared. What about the sector part? Well, that looks like this, and I need to know that angle theta. But this angle here is the same angle as that angle there, because they're opposite interior angles, or they're both complementary to that angle right there. So I need to know something about this angle theta. But notice that the opposite side over the hypotenuse side is just A. So that angle theta is the angle whose sine is A. And so the area of this sector piece is 1/2 r squared, radius is 1, times the angle, arc sine of A. So the total area that I'm looking for here is going to be 1/2 A times the square root of 1 minus A squared plus 1/2 arc sine of A. Kind of a complicated formula, but just based on things that we already know from geometry. You might want to try out that formula in two extreme cases. What if A equals 0? Is the area 0? What if A equals 1? Is the area pi over 4, 1/4 of the area inside the whole circle? Well, that brings us back to our question from a few minutes ago. How do we find the area under a curve like this parabola, something that's not made up of triangles or sectors of circles and things from geometry that we already know about? Well, that's what we'll be looking at in this second quarter of calculus, integral calculus. So the key question of integral calculus is, how do we find the area of a region under a curve? We can do that in special cases with things we know from geometry, but we have to develop some new calculus in order to answer the question more generally.